In this lesson, we're going to talk about how to graph reciprocal functions, specifically when the denominator is a linear function or a quadratic function. A reciprocal function is a function of the form y equals 1 over f of x. And we assume that f of x is a continuous curve. One way of graphing y equals 1 over x is to graph the function y equals f of x first, and then remember a few rules. The function y equals 1 over f of x is going to have a vertical asymptote at every x-intercept of f of x. And this is because an x-intercept of f of x implies f of x equals 0. So the function y equals 1 over f of x would have a denominator equal to 0, meaning there's a vertical asymptote. The graph of y equals f of x and y equals 1 over f of x will intersect at all points where f of x equals 1 or f of x equals negative 1. And this is because 1 over 1 equals 1 and 1 over negative 1 equals negative 1. Those are the two values for which the reciprocal equals the given value. The x-axis, third bullet point, will be a horizontal asymptote for the curve y equals 1 over f of x. This is in part because 1 over f of x cannot equal 0, and the numerator is always going to be 1, because the numerator is always going to be 1. So since 1 over f of x can't equal 0, then y can't equal 0. And that's part of the reason why we're going to have a horizontal asymptote at y equals 0, which is the x-axis. And finally, as the value of f of x increases, the value of 1 over f of x decreases. And as the value of f of x decreases, the value of 1 over f of x increases. This is due to the inverse nature of the reciprocal relationship. So think about it as x increases from 3 to 4 to 5 to 6. F of x will be decreasing from 1 over 3 to 1 over 4 to 1 over 5 to 1 over 6. So summarizing those rules, we can say what you want to do is sketch the curve y equals f of x, then sketch, first bullet point, a vertical asymptote at every x-intercept. Then recall that the graph of the curve you sketched and 1 over f of x will intersect at all points where the y coordinate is 1 or negative 1. Remember that the x-axis will be a horizontal asymptote, and also that as f of x increases, 1 over f of x decreases, and vice versa. A couple of definitions for this section. A positive interval of a function is an interval where every point has a y value greater than 0. So we state all the values of x for which the curve is above the x-axis, or y is greater than 0. And a negative interval of a function is an interval in which every point has a y value less than 0. And we state the x values of the function for which the curve is below, the graph of the function is below the x-axis. So suppose we wanted to graph the curve y equals 1 over 2x minus 6. And then we wanted to state some requested information. Well, the first thing we would do, according to our current method that we're going to try, is graph the function y equals 2x minus 6. In other words, sort of ignore that 1 over and just graph 2x minus 6. Well, using grade 9 methods, we see that the function would look like that. Now, to go through step by step, we would see that we want to sketch a vertical asymptote at the x-intercept of that curve. There we go. Now, we also remember that we want to make a point of indicating every point on the curve we just drew, on the graph we just drew, with a y-coordinate of either 1 or negative 1. Well, those are the points that I just indicated in red, and there they are. Now, we want to graph the curve, and we need to remember that when the original function increases, the curve that we're graphing will decrease, and vice versa. And remember that we can't cross an asymptote. So we're going to be going up into this vertical asymptote and then down into the horizontal, whoops, and then into that vertical and into that horizontal asymptote. But we can't touch the asymptotes. And so we're going to end up with a curve that looks like this. Okay, now if we want to really be particular, which is good, we can get rid of the diagonal line because that's not actually part of the curve. Y equals 1 over 2x minus 6. And now we're going to state the domain and range. Well, we see that the domain is equal to the set of all x element of the real such that x can't equal 3. The range is the set of all y element of the real such that y can't equal 0. Now, for our increasing intervals, we have none, but we do have a couple of decreasing intervals. Don't look at this arrow or this arrow and say that we have increasing intervals there. That's not how it works. Just as a reminder of these increasing and decreasing intervals, what it means is take any point on the curve and imagine a very small step to the right. Would you be going up or down? And no matter where you are on the curve, if you take a very small step to the right, you will go down. So every x value is part of a decreasing interval. But we cannot say x equals 3 is part of that because the curve is not defined there. Okay, now for positive intervals, this is this part of the curve. That part of the curve, every point is above the x-axis. So for all those x values, they are producing a positive y value. So that is your positive interval. And your negative interval is negative infinity to 3, because if you take any value from negative infinity to 3 as your x coordinate, you will get a point on the curve below the x-axis. But we have to use round brackets on the 3 because we can't include them because the curve's not defined there. We have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 3. All right, let's try another one here. Let's graph this curve. We see this might be a little more challenging because we have a quadratic denominator. So we want to graph the curve to start. We want to just graph y equals x squared minus 6x plus 5. So we have to go back a few years to grade 10 and remember how to do that. Well, we can factor, and we realize that that curve will have x-intercepts at 1 and at 5. And it will have a vertex at 3, negative 4. So we can sketch the parabola that meets those conditions. Okay? Now that we've sketched that parabola, we remember we want to draw a vertical asymptote at every x-intercept, like that. We remember that we want to indicate every point on the curve with a y value of 1 or a y value of negative 1 because we need to cross that parabola at those points. So we indicate those points on our curve. Now, the left and the right portions often don't give people as much difficulty as that middle portion. For this left portion, we just have to remember that we need to treat each of those, asymptotes as an asymptote. As the blue curve goes up, the red curve goes down, and as the blue curve goes down, the red curve goes up. Well, so not doing a great job there, but you can, and now, so it'll look like that. And we will also have to sketch something in the middle here. There will be something sketched in the middle portion right here, as we'll show you later. But what we're about to do is show you a little way of thinking about this. Imagine, just focus only on the vertical asymptotes and the horizontal asymptote. Don't consider the y-axis at all for a second. And if you think about it that way, we've got we've got a region that I'll call region 1, region 2, region 3. Another region we'll call region 4, region 5, and region 6. Okay? Now, we're never going to cross an asymptote in these kind of questions. So that means that when we actually sketch the curve in region 1 and in region 3, we won't cross over into region 2. So we're going to keep this region blank because that region, the parabola itself did not enter that region, so neither will 1 over f of x. Similarly, if you look in region 4, which is everything out here, and region 6, which is everything out here, we see that the parabola itself doesn't go into those regions, and so neither will the curve that we're about to draw. But the parabola does enter into region 5, so we're going to make sure that the curve that we draw, 1 over f of x, will also go into region 5. Okay, so we indicate 4, 6, and 2. Those are out of service for us. And now again, focusing on the left-hand upper portion, we want to make sure that we draw a curve that goes through the indicated point and treats these asymptotes like asymptotes. And so when we do that, we get a curve that looks like that. Then looking at the part of the curve on the upper right, we want to make sure that we treat those asymptotes like asymptotes, and we get a curve that looks like that. Now the middle portion is where it's going to get interesting. And in that middle portion, what we're going to do, we're going to treat the asymptotes like asymptotes. So we know we're not going to cross either of those vertical asymptotes, and we know that we're not going to cross the x-axis either. And we know that whatever curve we draw is going to have to go through here and is going to have to go through here. Well, we can guess that because we've got a vertical asymptote at x equals 1, we can guess that the curve will go down this way. And because we have a vertical asymptote at x equals 5, we'll guess that the curve can go down that way as well. But we're kind of curious what's going to happen in the middle here. Okay, what's going to happen in this portion? How do we draw that? Well, in order to do that, we have to use a little bit of logic. The curve y equals f of x has a minimum at 3, -4. Well, if I change f of x to 1 over f of x, then the word minimum becomes the word maximum. And leaving the x-coordinate alone at 3, the y-coordinate, which is often called f of x, we're now calling it 1 over f of x. And so what we're going to say is that the curve y equals 1 over f of x will have a maximum at 3, -1 over 4. So what we're going to end up doing is we're going to have a point right here at 3, 1 over -4, and we're going to draw, that's not the best job ever, but we're going to draw a curve that looks like that. Okay? And when we draw that curve, we get something that looks like this. And so now that's what the actual curve looks like. We can erase the portions that said 2, 4, and 6, obviously. That was just to remind us not to let our curve go into those regions. And we can, if we really want to, erase the parabola itself. And we have a function that looks like this. Now, we want to now start answering the questions given. What is the domain and range? Well, the domain is easy for a lot of students to see. They say, okay, there's a vertical asymptote at 1 and a vertical asymptote at 5, so there's my domain. Now, for the range, a lot of times students will say simply the range is y can't equal 0. But that's incorrect, because there's actually, if you notice here, a little blank space right in between a y value of 0 and -1/4. So we see that the range is y less than or equal to -1/4, and that explains this part. But then also y greater than 0, which explains the other two portions of the curve. And for any values in between 0 and -1/4, they cannot have a y value, so they're not in the range. Now, our increasing intervals, we see as we go from -∞ to 1, our curve is increasing to the left. And as we go from 1 to 3, our curve is increasing to the left. You can include your textbook allows you to put a round bracket on the 3. To my way of thinking, there's a square bracket around the 3, but I'll accept either for purposes of your test. Your decreasing intervals are going to be anything from an x value of 3 to 5, and so you can put a round bracket on the you can put a round bracket on the 3 or a closed bracket on the 3. I'll accept either, even though I think it's a closed bracket, a square bracket. You have to have a round bracket on the 5 because the curve's not defined at x equals 5. And then another decreasing interval is on the upper right as x goes from 5 to infinity. Okay, so your decreasing intervals are shown there. Now you have a positive interval on the upper left and on the upper right. So as x goes from negative infinity to 1 or from 5 to infinity, you're in a positive interval. You only have one negative interval, which is from 1 to 5. That's the lower part. And we have a horizontal asymptote at y equals 0 and vertical asymptotes at x equals 1 and x equals 5. All right, now imagine we wanted to graph this curve, y equals 1 over x squared minus 6x plus 9. We want to state the domain and range and the other information requested. Well, the first thing we want to do is graph y equals x squared minus 6x plus 9. So we convert to vertex form. We have x minus 3 quantity squared. So we're going to have a parabola opening up with a vertex at 3, 0. Now we're going to have, to show you really quickly what's going to happen, we're going to have a vertical asymptote at x equals 3, because that corresponds to an x-intercept. We're going to go through the points where y equals 1 or where y equals negative 1. We're going to graph a curve that treats those asymptotes like asymptotes, and the curve will look like this. And from there, we're going to be able to say our domain, range, etc. So here we go in order. We sketch our vertical asymptote. Okay, we go to each point with a y value of 1 or negative 1. Now, we can look at these regions 1, 2, 3, and 4 if we wish. We can see that the parabola is in region 1 and in region 2, but is not in region 3 or in region 4. These regions are formed by only looking at the intersection of the vertical asymptote and the horizontal asymptote and ignoring, don't look at the y-axis at all. That's irrelevant to this part of the analysis. We see that the curve that we're being asked to draw, 1 over f of x, should be in region 1 and in region 2, but not in region 3 or in region 4, because the parabola itself is not in region 3 or in region 4. Okay? And when we sketch the curve, treating those asymptotes like asymptotes, we get a curve that looks like that. If we are really being particular, we can erase the parabola from that, and the curve that we were asked to draw is simply this curve shown. Now our domain is the set of all x such that x can't equal 3, because that would make the denominator 0. And our y-coordinate has to be greater than 0, so that gives us our range. Our increasing interval is all x's from negative infinity to 3, and our decreasing interval is all x's from 3 to infinity. Our positive interval is going to be any x value in between negative infinity and positive 3, coupled with any x value from 3 to infinity. Now, we can't simply say from negative infinity to infinity because the function doesn't exist at x equals 3. Okay? So, it doesn't exist there. We do not have a negative interval. There's no point with a negative y coordinate. And we have a horizontal asymptote along the x-axis, y equals 0, and a vertical asymptote at x equals 3. We're going to graph this one as our last one for this video. We have y equals 1 over x squared minus 6x plus 11. Well, we can see by using the quadratic formula that there are no x-intercepts there. Another way of doing that would be to simply find the vertex and realize that the curve opens up. The vertex is at 3, 2, and it opens up. So now we've sketched the curve y equals x squared minus 6x plus 11. We want to know well, is this does this have any um, vertical asymptotes? And since the parabola that we just drew has no x-intercepts, therefore 1 over f of x that we're asked to graph will have no vertical asymptotes. And so there's going to be a horizontal asymptote along the x-axis because there always is. And after we've determined what our asymptotes are, we usually indicate any points on the curve shown where the y value is 1 or -1. But this curve has no y values of 1 or -1. So there's going to be no points of intersection between these two curves. They will not intersect at all. But finally, we can look at the region 1, region 2 analysis. There's no vertical asymptote, so really all we have, we're ignoring the y-axis for this part of our analysis, all we have is a horizontal asymptote, and so we've got two regions, the part above and the part below that horizontal asymptote. Well, the parabola itself is in region 1 entirely, so the curve that we draw will also be in region 1 entirely. That's another way of saying our curve better not venture below that x-axis. Okay, now one more thing we're going to do is we're going to recall this sentence. The curve y equals x squared minus 6x plus 11 has a minimum at 3, 2. Well, now I want to graph 1 over x squared minus 6x plus 11. Since there's an inverse relationship, that means the word minimum better change to the word maximum. My x stays the same, but my y, instead of being f of x, becomes 1 over f of x. So what I'm going to do is I'm going to draw a curve that has a maximum at 3, 1/2. And there are no vertical asymptotes, but there is a horizontal asymptote at y equals 0. As this curve goes up, the curve I'm being asked to draw will need to go down, but never cross the x-axis. And as this curve goes up, the curve I'm being asked to draw better go down, but never cross the x-axis. So believe it or not, the curve that we're about to draw simply looks like that. Okay. So we show the point 3, 1/2, and we sketch the curve. And if you want to think of it as a mustache, that's kind of cool. But anyway, getting on with this solution, we want to state what's the domain. Well, there are no undefined values of x, so the domain is x element of the reals. The range will be any y value between 0 and 1/2. We include 1/2 because there actually is a point with a y coordinate of 1/2, but we do not include 0. So this is a less than, even though that's a less than or equal to. The increasing interval, well, we see our curve as we go to the right is increasing all along here. So we would say the increasing interval is from -∞ to 3, or from -∞ to 3 with a closed bracket on the 3. Either is acceptable. I think it should be a square bracket, but your textbook puts a round bracket. And the decreasing interval will be all x values from that x value of 3 on to infinity. And I think there should be a square bracket on the 3, but your textbook puts a round bracket, so I'll accept either. Your positive interval, that means the interval of x values over which you get a positive y value. Well, that's from -∞ to infinity. Every real number imaginable will give you a positive y coordinate. There is no negative interval. We have a horizontal asymptote at y equals 0, and we have no vertical asymptotes. Okay, and we're going to do these other curves in a later presentation. So